you. Okay, so today we have the pleasure to have Associate Professor Dr. Carolina Pagli from the University of Pisa, and she will discuss magma chamber deformation and faults in East Africa. So Carolina, the floor is yours.
Thank you, and good afternoon, everyone. Thank you for coming. And yes, in this seminar, I will tell you about different sources of magma deformation, either magma chambers or deeper down, and also examples of faulting in East Africa. And regarding the methods, most of the studies are done with InSAR, which is a satellite-based technique, but we also compare and combine with other geophysical methods like seismicity and MT. Okay, so a little bit of a summary. The study area where the examples are sourced is the divergent plate boundary in East Africa. And here, obviously, the processes that we can witness are mainly the deformation caused by magma motions at various depths, and also faulting. That obviously all that occurs as a response to the plate extension. So the examples that I'll present are first about how magma flows from deep in the mantle into the crust. And on this process, I'll use an example of an inter-study of deep seal intrusions in IIFR. And then I'll move on to showing you what happened to the magma once it has finally migrated into the crust and it starts ponding, forming magma chambers, and therefore also causing deformation. And I'll show you a study of the Tulumoye volcano and geothermal areas in the main Ethiopian rift, so be further south. And then finally, we'll take onto an example of brittle faulting, of earthquake deformation that also can occur in a rift segment without necessarily the involvement of magma. And for this example, again, we will use InSAR and seismicity as well, other geophysics. And it's the study of a seismic sequence that occurred in northern IIFR not very long ago, in fact, just a couple of years ago. But let's go to see where is and what occurs in East Africa. It's this area practically that is the focus of the seminar, and it's an area of plate divergence. In particular, three divergent plates are involved: Nubia to the west, Arabia, and Somalia. And the divergence of three different plates has really created what is a triple junction and the formation of three rift branches. The one to the north, which is the Red Sea Rift, and the one to the east, this one, the Gulf of Aden Rift, and finally the one to the south, this one, the main Ethiopian Rift. And the example I'm going to show, they all come from different segment or portion of this plate boundary, either in IIFR or in the main Ethiopian Rift. Let's watch it in a little bit more detail, at least the area that we are going to present. The IIFR, it's a very depressed area that has been formed in the last about 30 million years. So it's the older sector of the divergent of the East Africa triple junction. And here the extension also is the highest. And in fact, if you take fixed Nubia and the full spreading extension of Arabia reaches 20 millimeters per year in Central IIFR at about this latitude. While if we go north, then the extension between Arabia and Nubia decreases, and there's a bit of a rotation also of this sector of the plate, and it decreases to, like, say, about 10 millimeters per year further north. The other sector, which is this one instead, this is the portion that accommodates the extension between Nubia and Somalia, and this is younger. In fact, extension occurred in the past 10 to 20 million years, And the extension rate not only, it's also lower. It goes from 6 to maybe 5 millimeters per year, depending on which latitude you are, but much, much lower than what we see in IIFR. And in fact, you know, the topography testifies this. You know, IIFR is a big depressed area. Instead, the main Ethiopian rift so far is a narrow rift. What do we see? What kind of processes can we observe? Well, because the plate diverge, obviously, the obvious thing is that at the surface, the axis of the plate boundary is marked by an area that is extensively faulted and fractured. And here you see a photo of the Dabahu Rift on the rift axis, where you can really see that the extension is ripping apart the crust, leading to the formation of normal faults, but also an intricate set of fractures. And together, so with the brittle deformation, we also have upwelling of magma from the asthenosphere, upwelling and formation at different level in the crust of magma chamber. One of the most famous here is the Ertale lava lake, which is one of the few permanent lava lake on our planet. So, well, we know when you see a lava lake, you know that magma chamber can become very shallow in the crust. And another important process that occurs when magma moves in the crust, it's not only that then from there feeds eruption on intrusions, but it also becomes an important source of heat that can be for us exploited to produce energy. And so there's a lot of geothermal manifestation here. I'm showing a photo of Dallo that really testifies that in this area magma is at depth level, and then it migrates and it becomes very shallow. Something about the method, because I'm going to show you a lot of InSAR in this seminar. So how does the technique work? InSAR is practically based on the combination of satellite images. So there are, if you don't know, continuously these SAR satellites that continuously orbit our planet. And they revisit the same area cyclically, and every time they acquire an image. So, and what does this image contain? Well, the measurement that the SAR satellites do is to measure very precisely the distance between the satellite itself and the surface of the Earth. Okay, so practically we have a measurement of this distance, like in the sketch. Now you can think that since the satellite, they continuously orbit the Earth, let's assume that at some point at time A, the satellite will make an acquisition over, let's say, an active volcano, and at time A, it will precisely measure this distance. The distance also in the InSAR lingo is called range, and it's the distance measured in the satellite geometry. So if let's assume that later, after a month or after some time, let's call it at time B, the satellite will revisit the same area and make the same exact measurement. In this example, our potential volcano has inflated. Say you have received some inflow of magma from depth, and in response, the Earth has inflated and sort of bulged up. So the satellite will make the exact same measurement. But this time, because the surface of the Earth has moved, obviously the distance that the satellite will measure will differ. Therefore, if we just combine together the acquisition made at time B and subtract the acquisition made at time A, we can have an estimate of all the ground movement that occurred between these two acquisitions. And that's exactly what InSAR is. An interferogram is a map of all the ground motions that occurred between the time of the two acquisitions. And so how do they look, these interferograms? They look very colorful because this ground motion that has been measured by the satellite is displayed as continuous cycles of color. For instance, let's take one cycle of color from, let's say, from blue to green to yellow to pink. And then again, it cyclically repeats. Blue, you see yellow, green, yellow, pink, and so forth. So what happens is that the total deformation is seen as a series of color cycles, which are called fringes. And one fringe, in this case, represents 2.5 centimeters of ground motion, either towards the satellite or away from it. So what we do to understand how the Earth moves is we count how many fringes. And then let's assume that here in the far field, you have your 0. If you start counting, say, let's assume the blue is the 0, then blue, green, yellow, pink. When we start again with the blue, we know we've reached a deformation of 2.8 centimeter. Then we count, and again, blue, green, yellow, pink, 5.6, and so forth. You count everything, and therefore, you finally have a continuous scale map view of the deformation that occurs. And it's interesting because you don't know the deformation just in one point, you know, in an image. So it's really a very powerful way of measuring the deformation field caused by really anything. And having said that, we need to remember that the satellite, they really measured only in one dimension. So InSAR is a one-dimensional measurement. So you measure the distance, you don't measure the vertical, you don't measure the horizontal, you measure along the satellite geometry. Now, given that the SAR satellite always have rather steep incidence angles, like in the sketch, they are more sensitive to the vertical component of the ground motion. But formally, you know, the motion where towards the satellite could occur in the horizontal or all in the vertical or a combination of both. And right because we have this ambiguity, that's why we like to not use only one interferogram where the satellite observed from a given geometry, but also from the other side. So typically we have the same area observed, let's say, in the two orbits. They're called ascending and descending, and they guarantee that the same area is watched from the east and the west. And in this way, we have two independent observations, and we can at least resolve the east-west and the vertical component of the 3D motions, while the north-south remains fairly unconstrained. So having said that, the interferogram, practically to generate an interferogram, we need two, as I said, two SAR images. And in the SAR images, we measure this distance between the satellite and the ground really by making a very precise measurement of the phase change. So the basic measurement of the SAR satellites are phase and amplitude. The phase is proportional to the distance. Instead, the amplitude is just the intensity of the backscattered signal and somewhat gives you an idea of the topography. It's not very much used, to be honest. So by combining the phases acquired at two different times, we can finally form the first interferogram. Obviously, this isn't perfect, and there are some contributions from the orbits and from the topography that needs to be removed, because at time 1 and at time 2, the acquisition will not be made by exactly the same point in space. So the orbits and the path that the signal follows won't be the same, and the topography will be seen from two different vantage angles. Therefore, there will be somewhat like a stereographic effect. So all these effects need to be removed, and they are routinely done in the production of a common interferogram. So at the beginning, you have something that looks like that, or lots of contribution. Then the correction starts being made, remove the orbits, remove the topography, until finally we have a product that's cleaned enough and can be interpreted in terms of ground motion. The other thing I wanted to say is that, okay, I made an example of the volcano, but really we can measure any ground motion you like. Like in this case, there's a fault, but people apply it to subsidence due to aquifer or landslides, practically anything that has a considerable ground motion of, say, a few millimeters, it's good enough for InSAR. But let's talk about where we apply this method. The first example is about how magma flows from the magma into the crust, because we know very well that during rifting, magma got to move, quite large volumes, in fact, of magma move from deep in the mantle into the crust. For instance, in the Dabahu rifting episode, magma moved into the intrusion by cubic kilometers, order of d cubic kilometers. So where does this magma come from? Where is it during an interrifting? We never see it. We have a fairly good understanding of how magma ponds in the crust at a different level, but how does magma really goes from the mantle into the different level of the crust, that remains very difficult to observe. And I'm going to show you a study, one of the few one, I think, to my knowledge, that has studied this process. We targeted in particularly Central IIFR because in this area, the extension is quite high. We said 20 millimeters per year. And there are a series of graben, Dabahu, here's Mandararo, Dendobi, Mino, various names, and Asalgabat, that accommodate the extension. Only Dabahu and Asal, they have volcanoes at the surface. The other graben that you see better here, that seems to be tectonic, or at least we thought they were mainly extensional tectonic features. And here, the advantage is that we don't have crustal magma chambers, so it's a good opportunity to see the potential impact of magma flow from depth without having the aggravation of the deformation from a shallow magma chamber. So we thought that was an ideal area to study how magma moves from mantle to shallower depth. Here, how do we combine together all these interferograms that I told you about before? We tend to have a same study area, as I said, observed in two different geometry. Once from watching from the west to the east, and again from the east to the west. So two orbits called normally ascending and descending. And then in these two observational area, we try to form all the possible interferograms that are available to us, and this is what we formed, spanning the time of 2015 to 2021. The next step is actually these single interferograms. They have been cleaned from some artifacts, but not all. And in fact, they have their own level of noise, like all geophysical measurements. So we don't take them as such, but we get them through a time series analysis software with the purpose of minimizing whatever residual errors might affect the measurement. In particular, we remove systematically from all the series of interferograms the residual orbital error, topographic error, but more importantly, we try to remove the atmosphere because InSAR is sensitive to this type of artifacts and that can really alter the measurement. So we stack them all together in order to have a measurement of an average velocity map and also incremental time series and an estimate of the RMS misfit, which is another important thing. How well do we believe certain measurement? So we've done that in Central IIFR, and here you can see the average velocity map for the ascending and the descending orbit. And down below, I'm showing you the time series, so of a few selected points, 1, 2, 3, 4, where I show you the kinematics, if you want, the dynamic behavior of only a few points between 2015 and 2021. So what are we seeing here? In the average velocity maps, we actually see that at the location of the asterisks, 1, 2, 4, we see red in both the maps. Red in this convention is the ground moving towards the satellite. So the distance between the satellite and the ground itself decreasing, and hence it's negative. So it's consistent with uplift. Also, if you see that in this case, we see always red, both when we watch from the right and from the left. That means that it can only be a vertical motion, because if it was a horizontal, if you look it from this direction, it would be moving towards you. But when you look from the other direction, it will be moving away from the satellite. So having these two orbits, it's important in InSAR. So what can we see? We can see that, okay, there's uplift at these 4 locations, which corresponds to 4 grabens. Here, I give you the name, if you're interested. Imino 1, the Relegagade the 2, Assal, and Alol. And here in these plots, you can see the dynamic behavior in the time, in the observational time. If you focus on these time series plot, it's better because there's better data. Here, there's a bit of a gap. Nevertheless, what we can see is that, okay, this is the average velocity, but it wasn't always going up. And in fact, it seems to have been a bit of an uplift at the beginning, then say rather stable until 2017, until finally the deformation picked up and continuously had the uplift until 2021. So we think that what we are getting here is that the uplift at these 4 locations are fairly distant from each other's was simultaneous. Another step that we normally do is that because InSAR comes in the satellite geometry, it's not easy for us to visualize it in 3D. It's not easy for everyone. So there are now methods to combine different data from InSAR with the GPS and trying to extract the real 3-dimensional displacement field. It's done by dividing an area into triangle, then throwing in all the different data and the GPS. And then within the triangle, the only assumption is that velocity varies linearly. And then we can invert for the real 3D displacement at the nodes of each of the triangle. Of course, we do that in a velocity field inversion with the aid also of a smoothing factor, because sometimes in some triangle, you would have a lot of InSAR and some GPS. But in some other triangles, you will have nothing at all. So the smoothing factor is necessary to keep the inversion continuous. And now this is the first time really was applied in INFAR in 2014, but now we are much more advanced. And in fact, these are the results by the postdoc Alessandro La Rosa, which used a much finer triangular mesh at 3 kilometers posting, and he could get a much more detailed result. What we are seeing here is the 3 components of the displacement. So you're seeing the velocity in the east, then in the north, this one, and then in the vertical, this one. So in the east and the north, what you're seeing is practically the extension. That's very much northeast oriented. So you see the vast majority of it occurs in this component and somewhat in the north. But if you look at the vertical, we also see significant deformation here at the location of this rift. And that's the signal we're interested in because, I mean, the plate boundary, we sort of already know it's extending. And I'm showing here a zoom of the area and 3 cross-section across the uplift. Here it's the first profile at the Imino Graben, then at the Relegagade and Alol, and finally at Assal. So what we are clearly seeing is that if we zoom in, the uplift does correspond to the Graben, and it's about 5 millimeters per year. I know that that's quite small, but it occurs in ascending and in descending, and that's why we have it here. So although it's small, we think it is real. Once we had this confirmation that the uplift is real, we went back to the original interferograms and simply invert them, assuming deep magma chamber, sills-shaped magma chambers at different depths at the location of the main 4 deformation signal. And here you see our observation, the best fit model, and the residual. So we think that these 4 different sills can all explain the deformation. They are all oriented in the same direction, which corresponds also to the structure of the Graben. So we think there's quite a good agreement between structural evidences somehow and sill. Their depth is the most remarkable thing, though. Look at the depth here. In cross-section, the deeper sill is practically close to the moho at 20 to 30 kilometers depth. And the other three sills further east, they are still at the brittle ductile transition between 10 to 15 kilometers depth. And interestingly, we find a good agreement between our model and the VPVS ratio from seismic imaging. In fact, in this figure, you can see that where the measurements of VPVS ratio, they approach our model sill, indeed, the VPVS ratio is quite high, like in this point. And high VPVS ratio is suggesting presence of melt in the crust. And these in three instead, these are results from previous modeling of the presence of sill. So they are roughly in quite a good agreement of what we also can observe. So finally, based on this observation, we could reconstruct how the magma flows from the mantle to the crust. We think that these are a set of sills that are necessarily connected. The reason why we think they're connected is because the uplift was simultaneous. And although we don't see the deformation from the connection portion, we think that there must be some pressure connection between them, so that if magma is inflow in just one of them, then all the other react simultaneously. And this also showed us that the magma from the mantle into the crust is fed into episodes, because we clearly saw there was no deformation between 2017 and then when it all started, and the four sills simultaneously had uplift. So the conclusion is that the sills are connected and then the magma occurs in episodes. So this is one, it could stop tomorrow, it could go on, there could be more in the next 10 years. We just need to keep monitoring. And yes, now I'm going to tell you about another example that's quite dear to me, because it's a Tulumoyo volcanic complex. And it's one of the first time I studied the geothermal area. Now, it's not in the ICTP-EAIFR. This is in the main Ethiopian rift. So we're going further south. And the area structurally and volcanically is quite complex. You see there are calderas, all these nested calderas. There is the Tulumoyo volcano, which is kind of a low-lying volcano, but then Bereccia and Bora, all different single volcanoes that make up for the Tulumoyo complex. It's also an area of high hydrothermal activity and the site of geothermal exploitation. There's Reykjavik geothermal that started production, and the drilling site is exactly here. So we know that the volcano was very active because in the past it was studied with the previous SAR missions. So we knew that between 2004, and 2010, there was some uplift and subsidence. This was already modeled, and it was attributed to a magma chamber at 2.5 kilometers depth. And then there was another study that used the most recent measurements, so 2015 to 2020, and instead did witness an episode of uplift, but they didn't model it. They just assumed it was likely caused by the hydrothermal source that also is imaging the MT. This is the massive advantage when you study the geothermal area, that there is a lot of other geophysics you can have access to, and the MT, the magnetotelluric, is very important. In fact, you see that they see highly conductive bodies, say C1 and C3, that they are the, say, here is described the magma chamber. Then an area of geothermal activity and the cap that here is called C4. Okay, so the aim here was to have a better look at the InSAR, do time series and modeling, and then compare to the MT to understand is it magma, is it geothermal, what's the cause of the deformation. So again, here we used ascending and descending. We try to use everything available. Well, in this case, we had to do a map that goes from 2014 to 2017, because in some cases the acquisition stopped in 2017. So what you're seeing here is practically the same thing as shown before, all a series interferograms stuck together to get the average velocity. And as you can see, it shows uplift. the uplift is not centered at one of the volcano, but is between, here you have Tulumoye, here's Bora and Bereccia, and you see the concentric signal is really here. And if you have a look at the two cross section, it's fairly clear that that's all consistent with just simple uplift. So what we did then is have a look at the time series where we could. So this is a point, the red point, near to the maximum uplift, but not quite. So one time series in one track is fairly continuous. Instead, the other, I said, it interrupted in 2017 as clearly more noisy. But nevertheless, you see that, say, from mid-2015 is when the uplift started. It was very rapid at the beginning, then it decayed, but continues. We also compare to the earthquakes, and we see that the cumulative number of earthquakes, it sort of resembles the deformation. So we think there's fairly agreement with the fact that rapid uplift at the beginning and then sort of plateauing. So we inverted that again, because we want to know where is the source of deformation. And we inverted that assuming a seal-shaped magma chamber. We try different solutions. We sometimes impose the seal to be horizontal or let it free to have a dip. But the best fit solutions are very similar. The dip is about 0 to 11 degrees, so sub-horizontal. And we also were careful enough to estimate the error bars on our model parameters. And as an example, I'm showing them here. So each of the model parameters of our seal are plotted here below. So the location, lat long, depth, length and width of our rectangle, but also strike, deep, opening, and then we calculated based on the opening, the volume. So we see from this distribution that it's fairly bell-shaped. So we're confident that our best fit solution, which is marked with the solid line, is good. And then with the dashed line, you see instead the 90% confidence interval. Okay, that's just to say how we do the inversion. And then once we were fairly convinced that our seal is this one, as you can see, we plotted them in plan view. The pink is the horizontal seal and the white is the dipping one. They're very similar. They don't change very much while we plotted both. And the interesting thing is that this magma chamber, it's fairly narrow and long, and it's got an elongation direction sub-parallel also to the caldera elongation, and also consistent with the strike of the transverse faults that exist in the system. Another important thing is that the seismicity that's recorded in the area in 2016 and 2017 that you can see here in green actually occurs above our dike. Our seal. You see here that the majority of the microseismicity is exactly above our inferred seals. So we think that's that gives credits, in fact, to our model. This is what you expect. And in terms of comparing instead to the MT, that's maybe a little bit more puzzling because it's right in between our seal, between the two very resistive conductive areas, C1 and C3, so that are interpreted as partial melt in the MT. And so based on all these observations, we wanted to have a sketch that summarized our findings and put them together with the MT. And in fact, we think our seal is practically this one, where you see it's a sideways sort of sliver of magma that goes west into the west part of the Tulumoye system. And this is the deformation of the InSAR we would see at the surface, so between Bora, Bereccia, and Tulumoye, all here. And we think that the deformation is clearly a magma because it's 7.7 kilometers depth. It can't really be water. But we think that the elongation direction is probably controlled by the presence of these transverse faults that occur in the main Ethiopian rift, and that can channel both the magma or also some hydrothermal circulation. Instead, these red areas are practically reconstructed from the MT, and they are the main area of deep partial melt and the heat source. In fact, the drilling that Reykjavik geothermal does is in this area because there's the clay cap, so they don't like to drill where there is no cap. So the conclusion is that, well, we have a seal that's deforming, and that's the first time really was observed. And it's important because it shows that even the western part of your system can have a heat source, possibly of interest also for the geothermal exploitation. And finally, why in the past did we see uplift and subsidence? Now uplift. Well, one interpretation that's consistent also with what is observed at other hydrothermal systems is that now we are witnessing uplift because the system of magma is open. Magma comes into the system. So every so often we have a pulse of uplift. But we think that in the future, this likely will be degassing or and into the hydrothermal system. And therefore, once this occurs, we probably will see a phase of subsidence. So we conclude that alternating phases of uplift and subsidence geothermal area are likely caused by a phase of magma inflow followed by degassing of the hydrothermal system and flow into the hydrothermal manifestations. Now, the last example I want to show you is different because I want to show you that there's not just magma in a rift. There is also for earthquakes and not necessarily occurring with the involvement of magma. A wonderful example of this is a sequence that occurred in Northern ICTP-EAIFR. So we are moving again into this sector of the rift. And it's a seismic sequence that really lasted 1 year and had two main faulting events. One, a magnitude 5.5 here, and a year later, a 5.6 here. Now, this sequence was really anomalous because there was normal faulting without any involvement of magma. Now, you might find this is normal, but it's the opposite. For a rift, when there's a normal faulting earthquake, the vast majority of these normal faults are induced by dike intrusion. And in fact, here I'm showing you the sketch of dike intrusion and normal faulting as we witness it for the very many intrusions in Dabahu. So practically every time in a rift, there's a normal faulting earthquake, somebody deduced, oh, there must have been a dike, and this is a dike-induced normal faulting earthquake. Well, it was not. And I'll show you the InSAR that clearly captured that. But before that, I want to show you that the sequence that occurred in this sector was truly anomalous because this is the NAIC seismic catalog, and it shows all the seismicity that occurred in the area historically. And what you can see is that in red, you have this 1 year sequence with a cluster in Bada and then another one in Massawa, one in December 2022 and then in August 2023. And if we watch the number of earthquakes along the rift, you really see that the red is by far the dominating part of the seismicity. So this sector was like fairly quiet until these two seismic sequences occurred. They are also fairly different. The one to the south and the earlier ones is clearly started with a magnitude 5, and you see clearly from the deformation that this can be explained only with normal faulting earthquake. It has this peculiarity, the seismic sequence of Bada, because first we saw the fault slip of a plane dipping west. And this is the interferogram that we constructed. But then just a few days later, further north of the main fault plane, another fault slip, west dipping this time. So that the combination of the first and the second event have created a conjugate set of normal faulting or normal faults that define sort of a small graben. So we were lucky enough to have very many nice InSAR acquisition, and we can constrain very well these two faults. So we know exactly how much they are long, and we can calculate their geodetic moment. So the first one was the largest, this one, and it was a 5.6. The second one, this one, a 5.4. And this corresponds fairly well to what was recorded seismically, because the total seismic moment was about 5.7, so corresponding quite well to the total. But the interesting thing, if we look at the seismicity, we can really compare, is that the sequence indeed had some very large, the first 5.5, a few larger earthquakes, until then on the 29th, there was another 5.5 and another series of 4.6 earthquakes. So there were really two sets of seismic activity, and this nicely corresponds, we think, to the two fault patches that move. And what you could do also, once you have quite good data, is that we selected our best waveforms and we cross-correlated it to see if there was some similarities between the earthquake corresponding to the first fault and the earthquake corresponding to the second fault. And indeed, there is a very good agreement. In fact, what are you seeing in this photo is the cross-correlation of this waveform with all the subsequent ones. And therefore, where you see hot colors, that means that these group of waveform are quite similar between each other. And again, when you see these other group of similarities, that means that these waveforms are similar. So we clearly identify, even seismically, two groups of similarity that we think they correspond to the two fault patches. And also this is clearly an evidence that well, you can have a normal faulting earthquake and have them purely tectonics and clearly forming a graben without no involvement of magma or dike at depth. Now rapidly to the last sequence, the one of Massawa that occurred further north. That's also only tectonic. We see here the deformation, and that can't be a dike. Believe me, I mean, the deformation from a dike is just very different. And also the model tell us. But nevertheless, we see that's different from the other one in the way that we don't have a focus deformation. So we immediately understand that's got to be deeper. And in fact, both the seismic and the modeling of the InSAR show us that this time the fault wasn't reaching the surface, like the graben. This was a 7 kilometers depth signal. Now, when we try to do a joint inversion of the two observations, the ascending and the descending, here comes the surprise. Now, here what you are seeing here, this is the observed, okay, and sorry, this is the two observation, ascending and descending, and the model, okay, in the two viewing geometry and the residual. The difference between this group and this group is only that in this model, the fault is west dipping, okay? It's a low angle normal fault, west dipping. And the dashed line is where this fault encounters the surface. So because it's a low angle normal fault, obviously it will go fairly east. And instead, this other model is the best fit model, assuming an east dipping normal fault. This time is not a low angle normal fault. So what is the problem is that when I show you these two sets of models, you probably think I'm cheating because they look identical. Look at this model and this model, and this model and this model. There's hardly any difference that one can appreciate visually, but I'm not cheating. These are two different fault models. The problem is that when the fault is quite deep, we have a problem even with InSAR in understanding whether is a fault dipping this way or dipping the other way. Both faults are about a 6 kilometers depth. They are both C7/3, and they are both normal, and they both correspond to a magnitude 5.7. So for us, it's very difficult even with this observation and characteristic to decide which one is the correct one. The main difference is one fault is dipping 35 degrees to the west, and the other 57 to the east. Okay, so what I want to conclude about this sequence is that both Bada and Massawa are part of a sequence that was purely tectonic. Now, Bada formed a shallow graben, and we saw it. Massawa is a relatively deep fault, 7 kilometers, that slipped fully seismically, but based only on the seismic and on the deformation data, it's difficult to decide which one is the correct one. It could be either, really. But it doesn't matter really whether you prefer a low angle normal fault or a high angle normal fault. It's just the important take home message is that extensional fault can slip without magma. So the question is, how's that possible? Why sometimes you have magma and others not? Well, here the explanation could be either time or space. So if it's time, what I mean is that sometimes during the rifting cycle, you may have magma that has already moved into an episode and is a shallow depth. And once the extension then is got to be accommodated by faulting, then you have the dike as well, and you have an intrusion. So perhaps it's just a matter of time, and in Northern IIFR, there will be dike intrusion. Or the other explanation is that the lack of magma is not a matter of time. It's instead controlled by the extension that is not uniform in space. In fact, in Southern IIFR and Central IIFR, we have extension of 20 millimeters per year. But as we go north, like these events in Massawa and Bada, the extension is much less. You know, it could be half of that, of the 20 millimeters per year. So it's also possible instead that in area where the extension is lower, that there isn't very much magma budget available. So it could also be that the northern sector, the implication would be that the northern sector of IIFR is more subject to tectonic normal faulting with rare involvement of magma, whether the central IIFR, their magma is more widespread, either at shallow or at the higher depth level. So to conclude, my overall conclusion is that, well, intermeasurements can, the new missions today gave us lots of hope because we think we can really identify the deep magma motion, possibly from the mantle. It wasn't the case before. When I started doing InSAR and deformation measurement, seeing signals below the crustal magma chambers was considered practically impossible. But with the fact that InSAR missions are so long, and obviously the technical improvement are such that the interferograms are better quality, we can also think we have to appreciate this small signal. And regarding Tulumoye, I also think InSAR is not just a good method for deep signal, but also, and it's always been in that regard, quite useful to identify the geometry and the depth of magma chamber and how magma moves, you know, in the subsurface. This is obviously a challenge for all of us because we don't only want to understand how volcano works, what's the level of hazard. We also want to identify possible sources of heat because that's very important for our future and for the transition to a greener economy necessarily based on renewable or geothermal energy. So I think InSAR will have a major role to play into that as well. And finally, well, you don't need to love magma to use InSAR, and it can very successfully be applied to the deformation caused by earthquakes and compared to, you know, seismicity as we've done in Bada or other geophysical measurements. This is important because studying earthquakes, obviously, earthquakes have an hazard for humans as well. So it's important to be able to study, to assess them and minimize these hazards. So thank you, I'm finished. And if you have any questions.
Well, thank you very much, Carolina, for this very nice presentation and very interesting. I'm going to open the floor for questions. So you can either raise your arm or unmute yourself or put it in the chat. So I see that Hamea has raised his hand, so please go ahead.
Hi, Carolina. Thank you
Hi.
so much. It's really nice talk. My
Thanks.
question is, the seals you showed in the central IFR, what's their contribution in strain accommodation mechanism? Do they contribute, or do they simply
Yeah.
sit there?
No, I see why you're interested in that. Well, the seal, the deep seal, they like many volcanoes, they mainly cause deformation in the vertical. They have much less contribution in the horizontal. So because the strain tensor that we calculate from IFR and that we've published also in the paper, that's a horizontal. It's only a horizontal strain tensor. It doesn't take into account the vertical. My answer would be no.
Okay.
Doesn't play a major role in this sense.
Thank you.
Okay, we have Tim Wright.
Hi, Carolina. Great presentation. Nice to see you.
Okay, thanks.
And really good to see the kind of updates on these various mechanisms. I guess I also had a question about that central IFR deformation signal. First, well, maybe it's two parts. So I guess I'd expect that maybe if we compare to kind of Iceland, for example, where you have the stretching, tectonic stretching, you get subsidence. So I wonder whether you actually, if there is indeed sills being intruded, whether you actually need even more magma than your model suggests, because you're having to cancel out that subsidence that you would expect. And the second question was whether you thought about maybe any kind of viscoelastic relaxation type signals. I guess the last earthquakes were a long time ago, so we wouldn't necessarily expect any.
Do you mean the seismic relaxation for the Bada, for the northern sequence?
No, I'm thinking about, again, those the uplift signals, in that if there were long-lived uplift you might get from post-seismic, I think, the normal faulting earthquakes. But
yeah, I mean, okay, the first question regarding the sills, well, we modeled them in an elastic, conventional elastic half space. So in these regards, the seal, they always give you uplift. So the answer is, well, no, I didn't really think about it. But no, why do you say that it will get some subsidence in Iceland? I didn't grasp that thing. Can you say that again?
I'm just thinking back to the work that Ricky and Feinstein have done. We're looking at stretching across the rift there. You get some long-term subsidence, which I think, just sort of intuitively, if you're stretching some crust, you might expect some subsidence.
Yes, that's true. That's true. You could, yeah. Now I see what you're saying. That seems to be the case that in interrifting, when you stretch, you also have subsidence, and that's been observed in northern Iceland. They explain, though, with the rheological difference, it's not really with the subsidence due to magma, due to volume changes, if I remember correctly. Here, my idea is that well, you just have inflow of magma from the mantle, and then that's the dominant part of what you see. Maybe you don't have these rheological differences that can cause the subsidence. Yeah, didn't think very much about that. Sorry.
No, I'm just thinking maybe you need even more magma if you're having to cancel out any subsidence as well. So that's great.
Yes.
Thanks.
Yeah, maybe we could try model when you extend and have these subsidence and also the seal, and see how the volumes work out. Yeah, thanks.
Great, thank you.
And what was no, say that again about the seismic sequence.
I was thinking about post-seismic. We can carry on, but we should let other people ask questions.
Okay.
I can carry on if you like. We could discuss it for a while.
Now, I had a question a bit related to Tim. Actually, I was wondering what was the thickness of this dike, like the optimal thickness your model was giving, and what was the length of this seal?
Yes. Let me see. Yeah, there it is. I don't remember them by heart, so so the depth is this. So they sort of go 32 10 kilometers. Length and width are the size of the the Okada. And then, yes, the opening is fairly small because this is millimeters per year. So it's more 4 centimeters per year, this one. Okay.
So you're actually not inferring what is the thickness of the...
Yeah, the opening rate is the thickness of the sills.
Well, the thickness is in centimeter or millimeters, but it's not in a rate. That's
well, here we inverted the velocity. So if you can multiply by the years. I mean, how many years is that? From 2017 to 2021. Yeah, so
okay.
So I fix here, then you get the total
Yes.
thickness.
Yeah, okay, thanks.
Yeah.
Yeah, it doesn't look a lot.
No, they're quite small. The open is quite
yeah.
big.
It's just like
yes, it's gonna be a large seal with a very small opening. Yes, we did think about that.
Exactly. That's why I was intrigued. Okay, thanks. Okay, sorry, we have a comment in the chat from Ibrahim. Are they known listric faults that extend from the crust to the asthenosphere within the IIFR region East African system? If so, don't you think that they could play a role in the bringing of the magma from the asthenosphere to the different levels of the crust, with the magma occurring first at crystal mushes, asthenosphere, lower crust boundary?
Wait a second. I'm not anything.
Sorry, I've been too quick.
I just read it in my listric fault. Yes. Well, the answer is we do not see a contribution from this type of fault that could, sort of help conducting the magma. Nevertheless, in the example of Tulumoye, the seal has a strike and an elongation direction parallel to the transverse fault. So in that case, I would say yes, that there's a structural control that helps magma being channeled in a certain direction, but it's more lateral in this case. I wouldn't say from the that we have any evidence from the asthenosphere to the surface of magma being channeled along fault plane. That's all the deformation from the magma chambers. They are either moggy or seals, so Okada seals, not both.
Okay, thank you very much. Are there other comments or questions on the chat or live? No. Okay, so it looks like we have no further question. So I think we'll end it there, but I wanted to thank you, Carolina, for your great presentation, and also everyone who joined us today. Thank you very much.
Okay, thank you guys for inviting me, and yeah, have a nice day. Yeah.